recording. Okay, so we're recording. So now we know that this print is going to be finished in 5.5 hours in using 0.24 millimeter layers, which is kind of a mid to low setting, basically for quality wise. And you can really see the layers here. If I was in the rush and I really needed to pump it out fast, then I would be using that 0.6 millimeter nozzle. And I'll show you how to set up the printer in Cura so that it is indeed 0.6 millimeter nozzle. So the first thing I'll do is I'll jump back to prepare here. So there's prepare, preview, and monitor. I'll jump back to prepare, and here where it says Prusa i3 Mark III, I'll expand it and I'll choose add printer. Right? Add printer. There's something in the chat. Ooh, okay. Wait, I'll write it down. Ljungberg's 50 sec paint. Thank you. I will be using that. Moving on. Add then I will choose to add the network printer again. And I mean the one that's using the 0.6 millimeter nozzle is still a Prusa i3 Mark III printer, right? So I will be adding the same type of printer. Oops, Prusa 3D, Prusa i3 Mark III. You can either follow, or you can later. You'll be able to later on look at the YouTube video if you'll need to set it up for yourselves, so that you can print faster. So I'll just be setting up Prusa i3 Mark III, and I'll just change the printer name. Can't find the printer on the school's computer. Yeah, just another Prusa i3 Mark II. Are you in the Add Printer menu? Yes, so on the school's computers, there is only the option to choose Prusa i3 Mark II, and that is fine. Okay, so Prusa i3 Mark III and Mark III's, and just make sure that you change the name, the printer name to like 0.6 millimeter nozzle, so that the name is different from the, from the one that's using 0.4 millimeter nozzle. And that's it. You hit add. So this printer has been added. And now as I'm choosing between the printers here, I can see there's the Prusa i3 Mark III's and the one that has 0.6 millimeter nozzle. The thing is that it doesn't have 0.6 millimeter nozzle yet. I just named it that way. So what I need to do is I need to click Manage Printers. Manage Printers. And then I select my printer that has 0.6 millimeter nozzle. If it's not activated, I will press Activate button. If it is, we're good to go. And then I will click Machine Settings. I click that. And then here are all of the settings for the printer. You know, how big it is, and how big the hot end is, and is it a rectangular or elliptical build plate. By the way, what kind of G-code flavor it's using. I talked about G-code yesterday a little bit. And then we have here two tabs, Printer and Extruder. I will choose the Extruder tab. And here, finally, we can see nozzle size. So here I can change the nozzle size to 0.6 millimeters. So it's in the Extruder tab. Once I've done that, I hit close here, that's it. Now this printer is set up to have 0.6 millimeter nozzle. Let me quickly change the settings. Oh, and yesterday I've talked that you can never go higher than 70% of the diameter in height, of the nozzle diameter in height, meaning that for 0.4 times 0.7, you can never go higher than 0.28 millimeters in layer height, while for 0.6 times 0.7, this is the limit, 0.42, right? So here for layer height, I will just choose 0.4. Initial layer height, that's fine. I'll leave it at 0.2. And we can just, also let me just make sure that all other settings are the same. Generate support, 65. Travel, that's good. Z-hop, yeah. Cooling. So all of the other settings are exactly the same as we used before, except material, where the printing temperature is set to be 5 degrees hotter. It becomes orange. So it becomes orange when you type in 0.4. Huh. What the heck? Does it say anything? Can you slice? Are you using, okay, first of all, let's start from. Okay. First of all, let's start with edit printer. Okay, so when I manage the printers and I choose to go to machine settings, you didn't change anything here, did you? Right, in the overall printer settings. No, okay. But you did change the extruder. There you go. So you need to go to extruder 1 and you need to change the nozzle size to 0.6. Then it's not going to complain about the layers being too thick. It's just basically complaining about the layers. It didn't save it. That's okay. That is very, and it's just for you guys, huh? For some reason, for you to, oh, for everyone, doesn't save the nozzle. Wait. What if you change anything else? Nozzle offset X. What if you change that to like 5 millimeters? Does that save it? But it doesn't save, it doesn't let you change the nozzle size. Wait, are you using a comma instead of a point? Okay, that was my only guess. But wait, it saves both. So if you type in like, okay, that seems to be a little bit buggy there. But if it's not saving the nozzle size, then you need to apparently saved when used the comma, but not a point, Sure. Okay, so my answer for it is fiddle with it until it saves. You know, try nonsense values, try using a comma, try. What if I type in hello? No, it doesn't let me type in hello. Okay. Anyway, I guess let's keep going. Okay, sure. Let's keep going. So it's going to be orange if, let me, oh, we are recording, okay. So it's going to be orange if the layer height is equal or larger to the nozzle diameter, right? So if it's orange, then it means that your nozzle diameter wasn't changed properly. Okay, so we have that going on, right? Let me slice it up just to see what happens. Hit preview. So now it's 2 hours and 15 minutes instead of 5 hours and 33 minutes, right? So we just shaved off half of the time. It's not going to be the, you know, the perfect quality. The quality is going to be a little bit worse, but it's going to be much faster to print it, right? Simply because, first of all, you can lay plastic at a much wider, you know, surface area. Second of all is that you can use much higher layer heights. Make sense? Recording now, which brings me to the fact that these shell structures are always, well, not always, but most of the time, they are constructed by using a mesh and in like mesh underlying geometry. And in this case, they are, in most of the cases these days, they are used Kangaroo or Kiwi 3D or Rhino Walt are used to produce these kind of not necessarily dome shapes, but shell structures, right? So wood is also possible, plastics and so on. So every material is suitable to make these kind of shell structures. If it's wood that you're after, then you need to take a look at grid shells, and especially not just grid shells in general, but the detailing behind the grid shells, how those are, well, that's not helpful. Wait, let me find, there we go. How those kind of grid shells are being kind of joined up into a single structure. Which brings us to topology, right? So do I have anything open here that's about topology? No, I don't. So let me find it for you. Mesh topology, no, mesh geometry topology. So mesh topology is basically how many, not how many, but how the faces of the mesh, why is this, everything is a PNG? There we go. How are faces of the mesh arranged, right? On top of the surface, right? So how is the mesh being created? You can kind of, can I find mesh topology good versus bad? So for instance, something like this is, this would be a bad topology mesh because you have a lot of weird stuff going on. So you can't really see an underlying grid or anything like that. It's just, you know, a bunch of rectilinear faces that are doing their thing. Let me find, yeah, this is also something that would be considered bad topology, simply because, you know, it's just triangulated, a bunch of triangles that don't have a exact system, right? Well, here you can kind of see the system of, you know, how you would separate the mesh into parts, but it's not really great. Then you have n-gons, which I won't cover during these tutorials, but, oh, there we go. This is, I guess, the best example here. Bad topology, good topology. Now, since I kind of know what's going on here, it's hard for me to just tell you, that the left-hand side is bad and the right-hand side is good. But just, I want to hear from you. Do you see, how the right-hand side could be considered good topology, while the left-hand side could be is considered to be bad topology in terms of separating this face here into pieces, or even making a grid shell, structure. Yet it is more easy to read, but there's more stuff that's underlying it. So, but do you see the differences here? Sculpting wise, it's the same thing. When it comes down to actual movement, moving of the form, it's the same thing. And the angles are also, yeah. Oh, I like this. The angles here and here are identical as well. So the form, okay, let me rephrase it. The form in between these two guys, if we were to hide the lines for these two meshes, you couldn't be able to tell them apart. They would be identical. They would look identical. Yes, first of all, it's only rectangles. That is true. Smaller file size, not necessarily. The file size can be bigger. For instance, here, you can see that under the eyelid, there's much more density going on than here in the shitty topology version. So the file size doesn't matter. The angles don't matter. More easy to sculpt? No. And more easy to read? Yes. Okay, so it is the one on the right hand side is easier to read. The main thing is, why is it easy to read, right? It's because this whole thing, structural advantages, is something that comes from so there are, of course, structural advantages, but it's not a driving factor on how good topology is created. It's just something that comes from good topology. On the right-hand side, yes, it does have only rectangles, which is very nice to work with, because you don't need to mess around with two lists. Now I'm going to be working with just triangles, and kind of solve all of the triangles of the mesh, and then I'm going to be working with all of the rectangles of the mesh and solve them separately. So these, first of all, yes, good topology is you either have only triangles or you have only, rectangles. So you either have polygons with 4 corner points or with 3, not a mix between them. With some exceptions, but most of the time it needs to be this way. Second thing, and much more important thing, is that the polygons follow the curvature of the surface, right? Here on the left hand side, they kind of do, but then the lines start breaking apart, and they don't really follow the curvature, how the surface is bending that well. While here, all of the polygons are following the surface lines perfectly, right? In both directions. So the elements from which the shell, in this case, is produced are following these bending lines of the shell very closely. And this is what comes down to being good topology. There are more things, and I will talk about more things. But this is, I believe, one of the main, most important things, is that, first of all, it's only quads. Oh, by the way, when I say quads, I mean rectangular polygons. When I say tris, those are triangular polygons. This is just how they're called, tris and quads. So this guy on the right-hand side only has quads, while the guy on the left-hand side has tris and quads, so it's a bit messier. Well, if this is scary, then that's a yikes. There's have you seen the have you seen the UVW map of a face? Wait, this is better. Beautiful. So this is what would happen if you cut off the, am I recording this? Yeah, fine, I'll be recording this. This was what would happen if you cut off the skin of a head of a person and kind of unwrapped it flat. Fun stuff, fun stuff. Anyway, moving on. Only quads, right? So as the reason why we're doing all of our kangaroo stuff from these kind of rectangular patches is because we divide those patches into a grid, and that grid will produce only quad polygons, meaning that that part of the topology is taken care of by us specifying that we are only going to be using rectangular patches to start with, right? Let me show you how to set it up, because some of you, for some of you, it's not anchoring properly. So you have two surfaces here and you have two boxes here. So you just, at the start of the definition, where we have the surface input, you just select these two flat surfaces and you reference those in, like that. And then for these two boxes, you select them and you reference them in right next to the anchor. There's a BREP component for BREP inclusion test. This is where it checks which vertices it should anchor, and it will only anchor the vertices which are inside of the BREPs. So you just select those two boxes and reference those in here. And it should work now. Works for everyone? It doesn't work for Albert. What does it say? Which part doesn't work for you? You don't see any changes. Oh, it might be that you haven't installed a plugin or two. No, it might be that, okay, Albert, do you have, let's double check. Do you have this mesh from points component, which is in the group that says create meshes from grids, join them and clean them, mesh from points component? Oh, you were missing it. So you don't have that. But if you type in mesh from points, that's not how you mesh from points. Yes, if you type in mesh from points, so you have it now. Okay, then just close the Grasshopper file and don't save it. If you save it, it's going to save without the component. So close it and open it up again, and it should then all work. If you have it, then it should work. Okay, I'll continue on slowly, and then if it still doesn't work, let me know. So here we have this a very, very simple setup, right? We end up with this grid. And if I were to bake this grid out, bake, default, okay, kind of look at it. Yeah, let me just flip it over. If I look at it, this is something that has very clean topology, right? The bending of the surface, which plugin? It's Mesh Edit 2, I think. Mesh Edit Food for Rhino. So if you go to Food for Rhino, it's Mesh Edit plugin, and you just download Mesh Edit Tools 2. This guy right here. You download it, and there is going to be one green file. You unblock it, and it's going to work. Most of the stuff can be found in Food for Rhino except Cocoon. Okay, so this is something that would be considered clean topology, right? Let's let's look at it more closely, right? So the curvature, you can see that the curvature of the surface it's making a little bit of a saddle curvature here. So it's bending downwards a little bit, and here it's bending upwards. So it's like it's what's called a saddle surface. Saddle surface. Something like this, right? We're getting something close to this. So it means it has double curvature. And the nice thing about it is that, as I've shown you in the example with the scary face, here the polygons are also following the curvature of the mesh, right? So this is clean topology, and this was, I purposely made it clean for you, right? So if we continue doing, like working with this, let's say if I disconnect these two guys and kind of make a copy of the surface like so, and kind of reconnect three of them now. So all I did was just, now I'm using three surfaces rather than two, and I kind of re-reference the three surfaces here. You know, it still follows perfectly. And this is the strength of using a very controlled approach at the start to get clean topology. Another way to do this would be to create a surface like that and type in mesh, hit OK, and then kind of work with the mesh by rebuilding it and so on. Sorry, I messed up one bit. When you're creating a mesh from a surface, you can choose to have more initial grid quads. So you can choose to have 100. That didn't help at all. I don't know what's going on with the meshing in Rhino. It seems to be fucked up completely. Doesn't matter. We're using Grasshopper for meshing, so this works. Let me show you a few more things. So first of all, how do I do this? Let me clear values here and clear values here. So I just remove all of the, okay, that's good. How did I move the surface? I just moved it in Rhino. I just selected it and kind of used the arrow to move it. So now what I've done is yes, exactly. Now what I've done is I just right-clicked and cleared the values for all of my inputs from Rhino. And I'll try to make what's called the Mobius strip, right? Something that I've shown during the kangaroo part yesterday, Mobius strip. Something that you shouldn't do when working with these surfaces, with this kind of approach. So let's learn how to do a Mobius strip. Before I do that, I'll just bring this guy back here, like so, as it was before, and I'll just make a copy of one of the rectangles, like that. Okay. Something like this. And let me just make them vertical. So you should have something something similar to this. Now, if I want to connect these into just like this kind of cylinder, I could do blend SRF, blend surface, and select the first edge, select the second edge, hit OK. Select the first edge, select the second edge. You can see it twisting. That's how it should be. No, hit OK. So this is me trying to create a Mobius strip by just modeling. And you can see that, well, here the bend is really ugly. Well, if it doesn't twist, that's fine as well. It's just, if now we try to join all of them up, try to join, even if it doesn't twist, try to join all of them up into one shape. There's no twist command. Okay, let me then do it without blending, without twisting. Flip this one, blend surface from here to here. Oh, come on, blend surface from here to here. What the? Yes, it's just called blend surface. Blend. Now I'm baffled. Okay, sure. If I do it the other way around, it just works. Flip. So now if we, if you have something like this, and there's of course easier ways to model it, but if you have something like this, this is not a Mobius strip, right? Because you can see on my screen that the inside stays on the inside, the outside stays on the outside. But what would happen if we were to say that this is this surface right here, sorry, that this surface right here is rotated inwards? And let me delete these two, right? So both of the surfaces are looking at the same direction. And I will use blend surface again. And actually, I think we need two more surfaces. So I will be doing something like this. Okay, 4 surfaces arranged as a cross. And it's just copies of the same thing. Right? Because I'm trying to do something similar to this. Is there like a faster way to do this? One horizontal, one vertical. Oh, sorry. There is a faster way to do this. I don't need 4 surfaces. I just need sweep 1. Yeah, sweep 1 would also work, but I want to show it with the blend surface tool. So here, and if I were to say that this needs to connect with the bottom part, blend SRF. Now I'm just blabbing like that. Yeah, that's good. Like this. And then the top part needs to connect to the edge here, like that. No, other way. Other way. Why don't you bend? Oh my God. Now there needs to be a twist here. Now I can't, God damn it, I can't model out a freaking blend surface. Okay. Wait, teacher is trying to to figure out what the heck is going on. Can we just do this? Oh, we can do it that way. Okay. For now, let's just have it like so. Do all of you have this kind of shape? So basically, you just do one flat rectangle, not flat, but one rectangle that is horizontal, one rectangle that is vertical, and you just use blend surface to blend the left-hand side edge of the horizontal one with the bottom edge of the top one. Flip it to get it right. No. That's not what I'm trying to do. I just need, for now, I just need you to have this. So I assume you have it. Okay. Since no one's saying no. And then instead of using blend surface, because it tries to autocorrect too much, and doesn't let me do a Mobius strip, I will use blend CRV, blend curve. Blend curve, enter. And then it asks me, it works exactly the same way as blend surface, only that it works for curves. So it asks me to select the curves to blend. So I will select, for the vertical surface, I will select the curve that is on the inner edge here, right? This edge here. And then I will select the curve on the outer edge, this one here, for the horizontal surface, like that. Not like that at all. If you see something like this, then you need to flip one of those curves, right? So in this case, my curve 2, I want it to connect to the other side of the curve. So I'll just choose flip 2. Like, oh no, that's cancel, try again. Blend, curve, enter. Select curve to blend, inner edge, and then outer edge, like that. Hit OK. You get the curve. So with blend curve, you need to get a curve like this. The one that connects the inner edge with the outer edge here. Why is this problematic? And then we use blend curve again, blend curve. And this time we connect the outer edge with the inner edge, like that. So that's the second curve. Right, so we get two curves here. Right, then all we need to do with them is just loft, enter, okay. So finally we ended up doing a Mobius strip. This is not necessary to do together with me. This is for me to show you possible problematic areas that you might encounter later when you're going to be working with meshes. So we have this Mobius strip here, and let me join it up. And notice how there is one place where the back face, and I have colored the back faces through in the display tab here. I chose color back faces to be turned on and back face color to be blue, right? So the front face is gray and the back face is blue. And you notice how there's a seam, and there's always going to be a seam where the back face is touching the front face directly. So there's this kind of discontinuity between these two, like that. And if I were to try and offset the surface, try to offset them all, you know, solid yes, distance, whatever, distance 10. If I try to offset them, notice what happens here, right? It breaks. So in case of topology, accidentally creating a Mobius strip is easier than you think. And if that happens, then you need to rethink how your whole shape is made, right? How your whole shape works. Because think of it this way: if there's a guy who's walking along this line here, right? So he starts at this point. Let me do this. Print screen. Paste it here. Hello, paste, paste, paste. Okay, try again. Print screen. Paste. There we go. So if there is a guy somewhere here, right? And he's walking along this line on the surface, right? It's walking, walking, walking. Then notice how he is going to go on the opposite side of the surface here. And as he's done the perimeter, he's going to be, you know, located on the opposite side of the surface after one, you know, kind of perimeter. And then if he continues walking on the, so right now he's going on the opposite side of this the surface, here, 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 and then he's going to kind of arrive here and continue walking and arrive, you know, where he started off. So he needs to do two perimeters to go along. Okay, so this is what's called a single face surface, and it's something that you cannot, you know, work easily with. Come on, go away, Rhino. It's something that you cannot work easily with neither Rhino nor Grasshopper. There are ways of how to solve it, but it's a bit problematic. Said that, I could kind of explode this into, like, these are 4 surfaces, and those 4 surfaces still contain 4 corners each, right? So I can indeed choose them to be set multiple surfaces, choose them to be surfaces, you know, that are going to be referenced into my shape. And the mesh is still going to be created from them, just like that. And then I can kind of, let me try and create, let me try and create a few spheres. That's a cylinder. A few spheres so that I can lock a few points in place. Just to show you how Kangaroo would be treating this kind of surface. No, you don't need to follow this part. That's fine. This is just for me to show you. So I'm just locking this whole thing in a few places here and there. Just to show you the problematic parts. No, that's not where you reference in the anchoring points. This is where you reference them. Let me hide these surfaces for a bit. Kind of reset the simulation. And let me bake it out. Or I don't even need to bake it out. I can just decrease the gravity. To make it smooth out a little bit. Now I will just bake it. Just to show you that that kind of behavior transfers. Show, stop the simulation. Wait, just give me a second, clear values. Okay. That kind of behavior of a Mobius strip, which is here, still transfers to the relaxed mesh by the end of Kangaroo simulation, right? So you can't have that. This is what I would consider bad topology, right? So this is one of the things where all of the front faces need to connect to other front faces rather than, you know, at some place back face connecting to the front face. So that's important. And one last thing that I want to show before we'll have lunch. Back to these guys, and you should follow this part. Let's select the two red boxes here and just hit delete, just get rid of them for now. We have two surfaces here, right? Which are left. We have these two surfaces. If I select these two surfaces and type in points on, I can change their control points. So where we have the meeting point, the bottom meeting point between the two surfaces, I'll just move it up so that it's something like this. And then just hit escape to get rid of the control points, right? So this one you need to follow. So we have that, right? And then which enables me to create, and I'll just draw it with a polyline, and you should too, which enables me to create this F8, this rectangle here, right? And I can just use, you know, once I have drawn it as a polyline, I will just be using surface from 3 or 4 corner points, this tool right here, to just make it into a surface. And yeah, flip, doesn't matter. And then I'll just delete the curve for now. So make sure that you have something like this, right? 3 flat surfaces that are touching each other perfectly, and that's all you have. So every curve, any curve that you have drawn, you should be deleting it and just keeping the 3 surfaces. Let me know if this part doesn't work for someone. Mm-hmm. Yeah, like just working in top view in this case is smart. I worked in perspective view, but it's better to work in top view. Everything is flat right now. Here, everything is like completely flat. All right, let's continue. So we have these 3 patches, and I will just right click on the surface input, and I will just set multiple surfaces, you know, to reference them in. By the way, if you want to see the points, and you should be, usually I do that, I make sure that I see the points. That's the viewer-bird vertices component. Right after unify mesh normals, we have viewer-bird vertices component that shows you all of the points that are created within the mesh. Okay. So now let's just choose a few parts where we are going to lock it in place. So in this case, I will say, I will just draw a polyline and just make sure that you're in the correct layer. So anchor regions layer here. Anchor regions layer, the red one. And I will just draw polylines around the points which I want to lock in place. So let's say these 3 points right here. These 3 points on this edge here, on this corner here. These 3 points here. Come on. Yeah, sure. And 2 more. So these 3 points here. And these 3 points here. So let me zoom out a little bit and just show you which points I'm around which points I have created the polylines. Like that. These 5 polylines here. Oh, by the way, I'm not locking them to a single point. So I'm never going to use a single point for my anchor as my anchor, because if I lock a single point as an anchor, it's going to produce a infinitely sharp, this kind of spike, which, you know, the whole structure is going to rest on this kind of spike, and that has absolutely no, you know, there's no logic in doing it that way. You always need to lock at least 2 or 3 points in place so that, you know, the structure is resting on a line rather than a single point, just for, you know, structural purposes. Does that part, this is an important part, does it make sense? You know, not locking a single point, just so that it's, okay. I didn't add the anchors yet. Okay, that's good. So keep that in mind. So we have logged them. Oh, by the way, I'm showing you this with Kangaroo simply, and this doesn't just apply to Kangaroo. The topology, you know, stuff that I'm showing to you. This applies to any kind of geometry that you do, right? When you're dealing with NURBS polysurfaces or NURBS surfaces, you don't think about topology because they don't have topology, first of all. but you need to think about other things when working with, you know, lofts and trims and so on. Is it a trimmed surface? Is it an untrimmed surface? Are the edges continuous and so on? How does Catmull-Clark handle that? Handle what? Handle which part? Topology? Well, I'll be able to show you. Catmull-Clark will always make if it's so Catmull-Clark subdivision, if it's a single, let's think of it as a single tri and a single quad, right? So the way Catmull-Clark subdivision will work, at level 1, a tri is going to be divided up like so into 3 quads, and a quad is going to be divided up into 4 quads, like so. So that's level 1 of Catmull-Clark subdivision. Then level 2, immediately after level 1, you don't have any triangles left, you only have quads left because every triangle was divided up into 3 quads, meaning that then it's just going to treat everything in the same way. It's just going to produce 4 times more polygons. So this is level 2 of Catmull-Clark. Right. And then level 3 would look like that. And so on, right? Catmull-Clark never produces tris. No, it always it's quite useful to make sure that everything is made out of quads, but and it's a big but. The problem is that you sacrifice resolution for that, meaning that notice how by how much it, like the amount of polygons would increase if you use Catmull-Clark on some, you know, some already dense structure. So sometimes Catmull-Clark is not an option, you know, because the resolution would be just way too high. But yeah, Catmull-Clark is one of the ways of how to clean up topology just a little bit. If the topology is too messed up, then it won't work. So back to here. Where did I add the anchors? I didn't add the anchors yet. I just drew the curves. So if we, let's jump to the perspective view. Here, where it's the anchor group, you can see that now it's set to be, it's checking whether or not the points are inside of a B-rep rather than if the points are inside of a curve. And here we have a bunch of curves. So what do? We make these curves into polysurfaces by using extrude. Extrude, curve, enter. And here I will change a few things. First one is solid. I will turn that to yes, so that it caps the top and the bottom of my extrusions. And the second one, make sure that delete input is also set to yes, so that it gets rid of the curves that you've drawn and just, you know, leaves you with boxes. And the height of the extrusion doesn't really matter. It can be quite low, like that. So we get a bunch of boxes, right, from those curves. And I will just take those boxes and, well, I should explain this. Right now, the boxes are located directly on top of the points, right? So the points and the box, the bottom face of the box, they match up in position, meaning that the point is not, it's in some sort of a limbo. It's not really inside of the box and it's not really outside of the box. It's like a, you know, Schrodinger's cat situation going on here. So I will just take the boxes and just move them slightly down so that the points are definitely inside of the boxes. And then, yeah, then you just select the boxes here, right click, set multiple B-reps. They will get anchored down, run the simulation. I'll just increase the gravity a little bit more. Oh, it's a nice little shape that, who would have thought? Maybe even decrease the smoothing a little bit for it. Yeah, so that it bulges like that. It's nice to play around with it. And then I will just bake this bad boy out to show you one thing. Default, flip. So looking at the structure from the top and looking at, this is going to be a question for you. Looking at something like this, do you see anything in particular that might be strange? Not necessarily strange, but that kind of falls out of place. And that's correct. What's strange about it? The line in the middle, one line disappears. No, it doesn't. Oh wait. Doesn't follow the curves of the shape. There's 3 directions for the grid. It's straight. Frey gets a bonus point. Unfortunately, in Lund we have only pass or fail grades, so the bonus point doesn't matter. But I don't know, just 3D print yourself a medal or something like that, and hang it on the wall. Frey was correct. There's 3 directions for the grid. So a grid in itself, you know, it can go horizontally and it can go vertically, right? And in this case, you know, we have 3 grids and they all connect in the same, you know, at one point, which is here, this kind of a locus point here, right? Which means that the structure that you're going to get is going to be a grid that has 3 directions, right? So it can go towards time for Photoshop. There we go. So a grid that can go towards here, right? This is fine. Oh, messed up that line. This is fine. And then you can see that the grid is going through here and it's bending through here. So it needs to take care of 1, 2, 3 directions of bending, which means if this happens, this is absolutely clean topology. This is absolutely fine. There is only one thing, and it's this point right here. And this is a point that is called a singularity. Very interstellar of us, I know, but it is called like that. And if I look at mesh singularity, like what kind of singularities you can get from a mesh, you can always see that it's something where all of the grids are kind of meeting, right? A point where all of the grids are meeting is called a singularity. And there are equations that get rid of most of the singularities, but those are very ew. math, no, we don't like that. So we will not be using that. Instead, we will be embracing singularities, and that's fine. Can meshes have, yeah, like here, this example here. Why did it download for me? Is this a virus? Meshes can have multiple singularities, and they even have different classifications. So there's like, the red points are singularities that we have observed in our 3D model. The blue points in this case are pentagon. Is that pentagon 1, 2, 3, 4, 5? Yeah, pentagon singularities, where you have 5 faces being shared by the same vertex, by the same point. In this case, the way we can think of singularities is, where's my Photoshop? Control Z. This point right here, right? For instance, this point right here has 1, 2, 3, 4 faces that are connecting to it, right? Any other point on the mesh doesn't matter. This point right here has 1, 2, 3, 4 faces connecting to it. And then we have this bad boy here. 1, 2, 3. Only 3 faces are connecting to this. And this is, then it is considered a singularity. You know, it falls out of place, out of the whole grid. And immediately, if I were to divide this whole thing into stripes, and let me paste it again. So if I were to divide this whole thing into stripes, let's say, you know, we have a stripe going on here, we have a stripe going on here, and so on, right? So we have stripe, stripe, Control Z, stripe, stripe. I wonder if it's gonna work in this case. No, it's not. Stripe, stripe, and then a bend. Control Z. Control Z again. Come on. So bad. And suddenly, where we meet the singularity, it becomes weird, right? Because, okay, so we can kind of do it like so, I guess. But then this stripe would be doing this. And suddenly, our stripes are not fluid anymore, but rather they make a 90-degree turn, and we have no idea why, you know, when it happened and why it happened. And that's because of that singularity. So a singularity is a breaking point for this kind of stripe creation. And to kind of solve it, you need to be prepared to either break the mesh into parts or to kind of embrace it and say, okay, what if what if I use the singularity as a starting point, and I say that my stripes start from the singularity. So this is one stripe here, like that. That. Wait, am I doing it right? No, I'm not doing it right. Ah, crap. Control Z, Z, Control Z. Now I forgot how to solve the singularity. It's always this kind of a problem when trying to solve them. It's basically this thing. You have a stripe that's going here, you have another one that's crossing it and going here, and you have a third one that is crossing other two and going here. And then you need to, and then you need to kind of start crossing the stripes and solving them that way. When it comes down to, if you're doing a grid shell, for instance, if you're doing this out of wood, you don't really care. That's fine. There's a singularity, so what? It's still a a connection, and it's still okay. But if you're doing it out of mesh stripes, then it becomes problematic. You know, like Mark Forness example, where the very many, you know, if you're doing stuff like these, you know, out of stripes, and then you have I think he has a singularity somewhere there. Let's find a singularity in an existing building. That's even more fun. No, make it bigger. Open image. There we go. Print screen, print screen, print screen, print screen. Photoshop. Notice how here the stripes are doing, and here the stripes are doing, and here the stripes are going, and then you have a point here. That's a singularity. And in case of Mark Forness, since they are really cool and really, you know, like high level architects, they used the singularity for their advantage to be able to create this kind of a branching structure and to be able to distribute the flow of polygons into two branches. So everywhere where you have this kind of, let me minimize it. Everywhere where you have this branching of the structure, you will always have, like, look where my mouse is, you will always have singularities which take care of the branching part, because a grid by itself, you know, if it's just a rectangular grid, it won't be able to branch properly. So you will need to incorporate singularities. So it's not like again, topologically speaking, it's absolutely clean. But you need to be mindful that a singularity will break the grid into two parts, right? Which will become individual, and then you will be able to work with those parts separately. Like that, for instance, right? This still works, doesn't it? So those are very interesting things, at least for me, you know, to like looking at them. And there's one last thing that I want to check before we have lunch, and then after lunch we will continue. So with something like this, with a form like this, we have this mesh that we get. What if we want to do, question, is there a way to draw the 3 squares into 4 squares in order to get rid of singularities? If 3 squares are meeting at a single point, like in our example, then, oops, don't do that. And if you did, then refresh. If 3 squares are meeting at a single point, like in the example that I've shown you, then no, there is no way. You need to rethink the whole logic, but it's not a problem. Like again, the thing that I want to really specify is that a singularity, a single point, is not a problematic thing. It's just an area on a mesh that behaves slightly differently to other areas. There are benefits to it and there are drawbacks, but you just need to be mindful that singularities exist, right? If we have a structure like a grid on top of this, will the simulation respect it? So this is already a grid structure. I can show it to you like this. Viewer bird, transform, not the window, wait. Come on. Like that, and then transform. thicken like that. So this structure right here is already a grid, isn't it? And this grid is already somewhat optimized for the flow of the forces. So there's no need, when you're working with a mesh, there's no need on creating a separate grid structure on top of a mesh, because the polygon flow already takes care of that part for you. I'm not showing you how to make a grid right now, simply because it's all about the form right now. We will be learning how to make grids later. I want to see if this thing can be automatically separated into stripes, into those kind of structural stripes. So the thing that I've drawn in Photoshop, I want to see if it can be automatically separated through Grasshopper. Just to make sure that, you know, how will Grasshopper automatically work with a singularity, if it's just going to say no, or if it's going to say, yeah, okay, we can work around it. So the way it works is in Kangaroo 2 tab, under mesh, under mesh subtab, there's a tool that's called stripper. So now when you all will finish laughing, we can continue. Okay, so stripper. We'll be using this stripper tool to extract separate stripes of a mesh. Well, try to extract separate stripes of the mesh. So the mesh that has baked this, basically our final mesh, if I connect it to stripper, I can see that the output of it with a panel, the output of it is a mesh that has, not a mesh, but a list that has multiple meshes in it. Meaning that somehow this big mesh, a single mesh, was separated into parts. Okay, so that means this tool works, right, on my shape. And then what would happen if I were to say unroll or unroller? Unroll a strip of quads. Notice how it says quads. It means that it can only work with quad geometry, and this is exactly why. From the start, I haven't shown you how to work with tries, with triangular polygons, only with quads. So unroll a strip of quads. I'll connect it like so. Nice. And you can see all of these get flattened out. So it actually works. And let me, where it says geometry preview, you know, where you have the custom preview of the blue color, I will connect the unroller output to the custom preview instead of my original shape, like that. And hide everything else. Manga stuff. Not yet. It will though. So there is one last input that I want to show you, and it's the T input for the unroller. And if you hover over the T input, you can see how much to unroll. 0 keeps the original, 1 completely unrolls. So unrolling means it flattens out the strips, right? And suddenly the strips are ready to be laser cut, which is really nice. So 1 is completely unrolled. Okay, let's see how we can work with that. If I create a slider that is in between let's just create a slider by typing in 0.500 and hit enter. Automatically, it's going to create a slider between 0 and 1. If we do 0.500 and just connect it to the T input and see what happens. When the slider is at 0, we have the original shape. And as I start moving it up, all of the stripes get flattened out. Which then means that we can take each stripe. We have 3 minutes left, so I'll be fast about it. And if you want to check it out, you'll need to look at the YouTube video later on. So I'll just do it in 3 minutes. So we have separate stripes, and I know that those are flat. So I can get mesh edges, and you don't need to follow this part. Mesh edges, I'll get those, and I'll just get the naked edges of the mesh and join them up into closed closed polylines. So I get these kind of flatten them out. So I get the outer boundaries of each of the stripes, and I can get the area of them so that I get the center point, and area properties could not be solved. That's fine. I can get the polygon center of them instead. And the polygon centers are working, and I can ask for planarity. So basically, is the curve flat or not? And that planarity also gives me a plane, which I can use to for orientation purposes later on. But first of all, I want to create a line of planes flat on the ground. So that's going to be my XY plane. And I'll just create series of numbers. And for the origin, I will just construct point. 1.5 minutes left. I'll just construct point. And I'll just plug in the series of numbers into my Y so that I get 10 points. And actually, I need to know how many points I'm going to need. So I will just measure the list length like that, and plug that into the count. And my step size is going to be something like 100, I guess. Something like this. So I have a bunch of these planes, and then I can kind of use orient an object from one plane to the other. So orient an object from the flatness planes that we got from here, the curve planes that we got from here, to the origin planes here. And now I have all of my stripes laid out flat. And if I bake them out here as a default layer, all of these are just separate stripes. So if I were to, separate stripes. If I were to bake all of these out, it would be, laser cut these out, I could assemble them into one, into that dome that we had been recording. So while I'm going to blab about this, you should open up the file, the one that we were using yesterday, and we will continue on working with it. We don't need those. So there's actually not a lot of things to do anymore with this, with this approach. It's quite robust at this point. The main thing that I would like to focus on now is how do we move the control points, not control points, sorry, the anchor points down and up. So how do we change the place where the mesh is, resting? How do we change its height? And to do that, the first thing that I'm going to do is I'll get rid of the smoothing. because that takes too long to calculate. So where it says smooth and it has a strength, I'll just turn that down to 0 so that it's not smooth at all. Well, it is smooth, but it's not, it doesn't have a consistent curvature, or the mean of curvature is not 0. And what else do we do with it? That's fine. All of that is fine, 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 fine. Okay, I won't be changing anything else with it. So it's just smoothing that I want to fix. So now, once I've done that, I want to see, you know, what kind of stuff I'm working with. So I will be hiding the anchor regions like that. In Rhino, I'll be hiding the layers, disabling the preview of layers. So I'll be disabling the preview of the anchor regions, and also I'll be disabling the preview of patch surfaces, so that those are not in the way. What the heck is that? Some sort of a hexagon. Let me unlock it. We don't need that hexagon, so I'll just delete it. I don't, oh, it's probably from one of the older tutorials. So we have a surface here that's doing its thing, and we still see these curves here. Yeah, that's fine. I want to actually keep those curves as they are. So now I want to have the possibility to move each of these legs of the structure either up or down, right? And I want to have, like, how many legs do we have? 1, 2, 3, 4. We have 4 legs that are touching the ground. So I want to have like 4 sliders, and using those 4 sliders, I want to be able to move those legs up and down. So the first thing to do is to turn off the simulation, the solver. So I'll toggle it to be false, just so that when we mess around with the definition, it doesn't crash the simulation. And I'll just hit reset for now. Sorry. So it's going to be this kind of a flat, you know, flat mesh before relaxation. Okay. So we have done that. And now onto the anchors. So let's see how this anchoring definition works, like how this part works. We get all of the points of the mesh, right? Then we have these B-reps here, which are, you know, closed boxes. And all of the points that we had of the mesh, the ones that are inside of these B-reps are it's basically checking whether or not the points are inside or outside of the B-reps, and it's removing all of the ones that are outside, right? And then the next step is it's pulling those points onto the closest curve. So onto these curves here. Thus it creates new versions of these points on the curves. And then it uses those new points as the target for anchors. So it locks the points on the straight line in place, and immediately it snaps them to the closest point on the curve. Thus, once we run the simulation, you know, they just snap to the curve like that. Okay, so that's what's going on. And now I want to have the possibility to move these points down. But I mean, just moving all of them down is kind of simple. I can just use move tool and, you know, for the target points and just move them down. But the problem is that all of them are going to be moved down or up by the same value. But I want to have possibility to change that, let's say, this leg is moving up, this one is moving down, this one is staying, and this one is also moving up, or something like that. To be able to do that, I need to, first of all, separate the grouped points not grouped points, sorry. Separate the points which belong to this box from points that belong to this box, from points that belong to this box. So what I want to do is I want to create a data tree, right? So a list of lists. And one list of points would be all of the points that are located in this box. Another list would be all of the points that are located in this box, and so on, right? To be able to do that, the first step is where we are referencing in the boxes. I need those to come in rather than being a single list of boxes as they are now, data with 1 branches, 4 elements in a single branch. Instead of being a single list, I want to right click on it and choose graphed, which will force it to be data with 4 branches, right? Because we have 4 boxes and each box contains, each branch contains one box in it. What this does is when it checks whether or not all of these points, are inside the boxes, it will check for each box separately, completely separately, and it will create 4 lists for each of the boxes, right? So 1,413 points in total were checked for first box, second box, third box, and fourth box, right? So you get 4 times more answers, but after using the call, so after actually extracting only the points that are, sorry, only the points that are inside of the boxes, we will see that, okay, the first box has 9 points in it, second box has 9 points in it, third box has 18. Which one has 18? Yeah, this guy right here has 18 points in it, and last box, fourth box, has 25 points in it. In your case, it might be different values, but it doesn't matter. What matters is that right now, it's not just a single list of points, but rather it's 4 separate lists that are not aligning, or what's the word for it? That are referencing which box do the points belong to, right? And then it's the same thing, that then you get these points as separate lists and you pull them to the closest curve, same data tree, absolutely, and then you get anchors, right? So it seems like all we did was we just grafted the boxes, but without grafting them, actually I can show you this like that. Look at it this way. When they are grafted, output from the targets is data with 4 branches, right? So 4 boxes, everything is separated. If it's not grafted, if it's as we had before, it's just a single branch and all of the points, all of the anchoring points are in the same list and it doesn't matter which box they belong to. So by grafting, we're kind of introducing that information that, this point belongs to that box and this point belongs to that box and so on. We can use that. And we can use that by, if we were to use move function, move, and if we were moving the pulled points, these points that are on a curve, so I will just connect them like so. If we were moving them either up or down, that means our vector is going to be z, in z direction. So I'm just going to type in z, unit z, enter, connect it like so. And then I can I can create 4 sliders, right? So let me create a slider that's going to be between -100 ... 100. So a slider that can go between -100 until 100. Do that. Create a slider like that. and then just copy it 3 times. Control C, Control V, Control V, Control V. So I have 4 sliders, which will correspond to the point groups in each 4 of these boxes, right? So right now, all of them are set to be minus 100. That's fine. We'll mess around with them later. All of you did that? Hello? Anyone? What did I do to get the lines dotted? In the definition, I grafted the brep here. So then I have like 4 sliders, and how the heck do I use them to move, you know, separate groups of points here? Well, first of all, I need those sliders to come in as the same data structure as the data tree that I have here, right? So the first slider needs to come in as data branch 00, second slider as data branch 01, and so on. To do that, I can, well, let's do it in a simple way. Let's just use merge tool, and just connect slider 1 to D1, slider 2 to D2, slider 3 to D3, and slider 4 to D4, like that. So that's merge. What merge does, it just basically pushes everything into a single list, right? It's just a list of 4 numbers now. And if I change, you know, one of the sliders, the number in the list will change as well. Easy. But the problem is that this is, while this is a list of 4 numbers, it's not 4 separate branches. So how do you take every item in the list and put it in a separate branch? Oh, this is a question to you. Let's see if anyone knows. So how do you take each one of these numbers from the merge output and put them in a separate branch? Okay, list. I don't know what list means. List item, flatten, list item. Not yet. No. Try more. Entwine. Entwine actually would work. Oh, there we go, Max. Graphed. So now let me go through the answers. First of all, flatten. Axel, that's what I meant. No, you don't get to do that. Flatten does the opposite of graft. It takes separate branches and forces all of them to be the same list. And graft does the opposite. It takes every separate item on the list and puts them in a separate branch, each item. List item is very useful. List item is basically a reverse of merge, right? So if I were to use list item on this guy, list item, and let me actually like shuffle these values around so that they're not the same, and it's easier for you to see, you know, what's going to going on, what's going to be going on. If I were to take list item and I just connect it, you can see that it gives me the first item in the merge list, right? And then if I press the plus button, I can get the second item and so on. What if I just want the fourth item, but I don't want to keep, you know, especially if you have a list of 58 items, right? And you only want to get the item number 42 out of that list. You know, you won't be kind of pressing that button 58 times. No, instead you use a number for the index. Notice how here in the merge list output, there are indices 0, 1, 2, and 3. This is basically a numbering of the list, you know. The problem is that it always starts the list numbering from 0, which kind of messes with your head. So if I want to extract the last or the fourth item from the list, which is my slider which says -10, then into the I input, I would plug in -10, okay. -10, connect it, and then it gives me, phew, I don't plug in -10, I plug in 3, god damn it. I don't know where my mind went. Again, these indices represent the position of the different values in the list, right? So to get the fourth one, I need to put in the index 3, right? And then my list item will give me the output of this slider. Okay, so that's what list item is useful for. It's for extracting separating and extracting information from a list. Entwine, Kaiser said entwine, and that is also correct. So it's not just graphed, but entwine would be used instead of merge. Entwine. And if you connect it like so, right? It's the same thing as taking merge and using graphed for it. In this case, very, very important to note that it's, in this case, the same thing. If I were to check the data trees of the merge and the entwine, these are identical, right? If there are, let's say if D1 receives more than one number for some reason, then merge will stop working and only entwine will work. So entwine is actually a cleaner way to do this, but I wanted to show it with merge just so that I see how long it's gonna take you to guess graphed. But entwine is also a correct solution. Okay, so back to merge. Here we have a list, right? Data with one branch, you know, a single list. If I right click on the merge output and I choose graphed, data with 4 branches, you know, absolutely same data structure as we have for the points, meaning that for the point groups, meaning that the grafted output of the merge can be plugged in into the Z vector, like so. Where are we? There we go. There we go. So now you can already see, since I was messing around with the sliders, that this one kind of moves one group of points, second group of points, third group of points, fourth group of points, right? Which means instead of using the original pole point output for the target, we can use the move output for the target. Chat says something. Tobias is just doing. Okay. Anyway, so we're instead of using just pull point output, we're using the moved version of the pulled points. Yeah, parenting, well spoken. Let us reset and run the simulation and see how now I can control with these sliders. Now I can control how the structure behaves, you know, how high it gets and so on. Cool. Okay, let's start troubleshooting. So where did you pull the move to? I assume where did I connect the move to, right? It's the target for the anchor. And Andre, G2T. G2T, indeed. And Andre doesn't work. What about the dashed lines? So double check. Is your brep input grafted? And also is your mesh out, sorry, not mesh, merge output grafted? These two guys need to be grafted. So there needs to be an arrow sticking upwards between these two guys. Okay. So now we have possibility to also change the height of not the height, but the placement for the anchors on this kind of a structure. Yay. Then we can kind of turn on the smoothing a little bit, but honestly, smoothing seems to do more trouble than good. So if you really want to have some smoothing, then use the strength of 1, right? Don't overdo it with smoothing. No, strength of 1 is fine. So we end up having something like that. Let me quickly remodel a new version of this just because I got tired of this one. You don't need to follow through. This is just going to be me messing around with it a little bit. I'll just do something like this. Then I'll just grab these 2 points, move them here. Like these last tutorials are more of a chill out session rather than the actual, like decent tutorial to show. Something like that. And in doing it this way, it's very easy for me to create these kind of non-manifold edges. So I'm always making sure that it all connects correctly. Again, front face to front face, back face to back face. And it is going to, for me, it's going to break most of the time, until I'm finally, done with the structure. So let's say that's front face. What if these become front faces as well? So this bridge right here is done, and now I just need to take care of these two surfaces. So I'll just take that control point and move it. I don't see where am I moving it. Move it from that point to here. This control point, move it from that point to here. Okay, so that one is done. And then this one of 10 mm, move it here. Oh, and this one, simply move it here. And of course, just so that it's easier for me to see, I'll just flip it. Oh, so funky. Then I can, let me first grab the sliders and kind of move them closer to 0 somewhere. Unfortunately, there's no real, kind of snapping slider-wise that they just snap to 0. But, well, you can always, double click on them individually, type in 0, 0, 0, 0. You can always do that. That makes a fun sound as well. But other than that, there's no real way of how to work with that, how to snap those values. But here it seems like, yeah, that seems to be working. There's a crap ton of tension in this part of the structure now. So I think I will be, 10 minutes left. I think I will be removing that support in total. And this is going to be me just showing you how to change this definition so that it works for you, right? So I don't want to, first of all, I don't want to run the simulation as I'm changing things, so I'll stop it. I will be removing this box here, delete, and thus I don't need this curve anymore. I'll be removing this curve here. So I'm only left with these 3 curves and these 3 boxes. So I'll just re-reference them. 1, 2, 3, 3 boxes, go in here, set multiple boxes. 1, 2, 3, curves, go in here, set multiple curves. Don't need to do anything else. This is how it's gonna look like. Can we do something even more funky? Nah, I won't mess with it anymore. So now, since there's less anchoring involved, I don't need the load to be that big. So I'll decrease the vertex loads. A little bit like so. Maybe I will increase the length factor back to 1. Something like this. Some really weird shape. I don't know. Looks bad. Looks really bad. No, I hate it. Let me absolutely hate it. While I'm fixing it, do you have any questions? Yeah, go ahead.
Maybe it's easier to take it there. I don't know if it's kangaroo related, but I just wonder, or maybe it's too early in the process. but I just wonder how they like achieve these kind of like legs they have inside, because it feels like the outer shell is cocoon and the stretch is more like kangaroo. Or how is it a combination, or is it just kangaroo? Like you see those stretch legs or pillars.
Yeah, I understood the question. How are these achieved? So there's, well, it's hard to say about this project in particular. It might be, it not might be, it's probably a combination of the two, of cocoon and kangaroo. But in this case, this is heavily remeshed into something that has very clean topology. Meaning that the main problem is not it being cocoon or kangaroo. That's not problematic. The problematic part is how the hell do you achieve a clean topology out of these spheres, right? Because I assume you would have like an insane amount of singularities and so on here. But to answer the question, how do you do this, is basically you create this whole shape, right? Let's say in cocoon, and then you add to that shape a leg, right? You just model it in Rhino. Not a relaxed leg with mesh, but just a leg in Rhino, and then you can either use kangaroo to soften the transition between the leg and the blobby surface, or you can or you can straight up use Rhino to soften that. But the main thing is why I started talking about topology immediately when I saw this is that from cocoon, and these balls are probably done in cocoon.
Yeah.
From cocoon, the mesh that you get is just a soup of triangles. It doesn't make any sense. So the first thing that they've done, even probably without the leg, is they took this kind of metaball structure and they completely remodeled probably by hand, retopologized it. So made it out of quads, and all of the quads are following, certain directions and so on. And it's done constantly in the industry, right? Hand retopologization, hard word. And once they have done that, then where does this leg meets the cocoon shape is there? Yeah, there we go. Where this leg meets this kind of ball shape, they could kind of connect it in a clean way rather than trying to scramble between those kind of shitty triangles that you get from the cocoon mesh. So there's that kind of very important step in between, which is called retopologization, the hard word, hand remodeling everything so that you can put in a rectangular pipe here and smooth it out with, well, it's not rectangular. You can see in the bottom here, it's like octagonal or something like that. So that you can smooth it out with either, at that point, it doesn't matter. Is it kangaroo or is it just straight up Rhino smooth? It's all about topology. Hopefully that kind of answers the question. So first step is using cocoon to do the blobs and making them clean.
Yeah.
Okay. Are you going to show how to project a pattern along a surface? Yeah, I was thinking about that. A surface like the one we made. You're talking about this mesh here? I was thinking of doing that, but honestly, it's so early for that. Like, pattern is something that's, just ornamentic. It's just an ornament. I might show it. I will show it as the last step of all of these weeks. just so that you don't start doing a pattern without having a volume or without having a shape, because that is a very dangerous thing to do. You know, I'll start from a drawing that I'm going to have on my building, and then I'll just figure out what kind of building I'm going to have. That's easy. The drawing part is hard. Well, no, it's not. So that's going to be on during the late third week, so next week of these workshops, patterning. Honestly, so coming back to this one, to this method here, see how we have like 4 sliders, and this only has 3 boxes, like four anchors. It means that we don't need 1 slider, and you should always delete it. You know, always have the correct amount of sliders for movement in height. Always have a correct amount of sliders, because if you have too many, or even worse, if you have too little, then it might become problematic. Okay. Tomorrow we will not have any tutorials. So this one is the last one regarding kangaroo, but I will come back and show you the pattern by the end of next week. If you'll have any questions, just ask in the chat later on, and I'll make sure to answer them. Okay, we're done. What happens tomorrow? Wait, I'll write what happens tomorrow in the chat. Just so that we save time. Okay. Take care, guys. See ya. But for this kind of game of life script, for this workshop, at least for this week, you don't need to think about the floor slabs and the windows and the enclosures and so on. All you need to think about is the silhouette and the form, right? Because enclosing it and, you know, making it work as a building, or even solving the connection to the ground, is going to be taken care of next week and, you know, all remaining weeks after that. So right now what I'm going to be showing to you are going to be these kind of I'm going to be jumping the gun a little bit. I'm going to show you benefits of using this kind of structure, like future benefits of using this kind of structure once you will start developing into the building. But to repeat myself, you don't need to do that now, and you shouldn't be doing that now. Before I'll begin, I guess let's switch it up a bit, and I'll start off by asking, you know, is there anything about this that is not clear, or, you know, you're kind of on the verge of kind of understanding something but not really? I can go ahead and, you know, explain. Or if you're just interested in something that you would like to do with the structure and you're not sure if it's possible or not.
I had one thing. I tried to prepare like my first model for 3D printing yesterday, and all the holes that you have, it wants to generate supports in, and I have a feeling that it will be quite some work to get all of the supports out of all the different holes. Is it that just something you have to live with?
Yes. Okay. There's yes, there is this kind of problem. Well, it's not really a problematic, but since we're using this kind of voxel approach, it's going to have horizontal surfaces from time to time, especially, you know, where the holes are. It's going to have these horizontal surfaces, and those will generate support one way or the other, right? Because they're horizontal. You can't print, for instance, something like this on thin air. Said that, you will become quite handy with a screwdriver and perhaps a hammer, if you get what I mean.
Will it be very, like, will the remains of the supports be very visible, or can you get them all to just disappear?
They will be somewhat visible, yes, but nothing too concerning.
I didn't really understand that when you talked about the supports, that there's like a small gap between the supports and the actual, like, but if the printer manages to, so if the printer manages to make the like the overhang, then it won't need the support. Will it always never, like, fall down?
It will always sag at least a little bit.
Okay,
right?
so if you have like a tunnel, a perfect circular tunnel, it will always be a little bit flat in the top.
Just a tiny bit, just a tiny bit flat for sure. The 3D printer, let's say it like this: the gap between the supports and the model is one layer thick, right?
Yeah.
Which means that the 3D printer will, as it's printing above the support, for it not to, you know, not to touch the support, it needs to sag less than, let's say, 0.2 millimeters, which is not, you know, it is going to sag at least by 0.2 millimeters, if not more. So the supports are indeed holding the structure, but given that small gap, they're easier to break off. So first the support will break, and only then the model will break, right? So it introduces a weak point in the support, so that it's easier for you to remove it. So, you know, holes like these, very easy to remove supports. But there will be, well, actually in this structure there are none. In this structure it would be easy to remove supports all throughout. Let me bring one thing here, just a second. Apparently, my arms got fatter and now it doesn't fit, but wait, let me stop sharing. There we go. There's this bracelet thing, right? A weird thing. So removing the supports from this one was around 5 minutes.
Okay.
And you can't really, I mean, if I look closely, I can see the supports, but it's not about that, right? It's about, you know, it's not about can you see the, you know, remainders of the supports in the structure. It's more about, I really can't put it on.
So because like the model I have right now is the holes or the pores are such, they're like way smaller. Is it, should you make it so at least like a hole is no less than maybe half a centimeter in diameter? Or like how fine can you make it?
I mean, it comes down, and this is actually important when we talk about these kind of cellular structures. What is the size of a single voxel? You know, in reality, if this was a building, and it's, you know, it's made kind of out of these, where the heck am I drawing them? Here. Box, why can't I use, there we go. 10 by 10 by 10. So it's kind of made out of this step, right? Like the boxes of 10 by 10 by 10 units. What is, in reality, once this will become a building, what is this, you know? How big is this single cell? Is it a meter? Is it 5 meters? Is it 10 meters? right?
Mm.
And this is something that you need to decide on your own. If it's a meter, that means all of the openings. So I'm not talking about the 3D print, as you can see right now, but I'm rather talking about the form itself at the correct scale.
Yeah, yeah. So how much is one step in reality?
Yeah, because that's much more important than the 3D print. The 3D print, can you remove the supports, can you not? Doesn't matter, whatever, you know. If you can't remove some of the supports, that's not the end of the world. That's fine. Usually if you can't remove them, that means you can't see them. Or at least you can't see them that easily. But the thing is, you know, if this is a meter, let's say, that means that all of the nooks and crannies of the structure, and let me make it, no, that is fine, just, there we go. So all of the nooks and crannies of the structure are very small, right? If this is a meter, that means that a person is, you know, something like this big.
Yeah.
Which means that if I put a person in here, you know, this can act as a space, but you know, stuff like this cannot be a balcony, or, you know, suddenly the structure becomes, only parts of the structure become useful architecture-wise. If, let's say, the voxel is 10 meters, right? So I've just amped it up by 10. That means that the person in relation would be 10 times smaller. So let me scale him down to 0.1, something like that. So now that's the size of the person. And now you have another problem. And that problem is that the structure is way too big. The building is way too big. So then the question appears, what kind of size is just right? You know, if one is too small and you can't fit a person in the building anymore, and the other one is too big and the building is, you know, too large, the scale is too much, then what's the correct size? And it comes down to, again, to thinking about the building, or not the building, about the structure, in various different ways. So one of them is, if we look at it from the front, right? And we can see here that, you know, we had this grid of points. Are these different stories, you know, of the building? If these are different stories of the building, that means that the person is going to be, you know, something like this big. And then you can kind of locate the person and then look where he fits and where he doesn't. For instance, you know, if the person is this tall, and let me extrude curve. I can't extrude it. Let me just do something like this real quick. There we go. If that's a person and I place him here, then yeah, he can use this opening, for instance, as a tunnel. So you can treat like these points as different levels of the building, stories of the building. Or you can say that, no, actually a story is every other point, right? So every two levels of points, there's a story. But that would mean that then the person will start bumping his head in certain places, which might be fine. You know, why not? Because other places will be left open for the person. But then you will need to do much more culling, not culling, what's the word for it? Boolean differencing, you know, to be able to fit the spaces in. So there's, I've already said this, but there is going to be a lot of modeling involved. Well, with any kind of building, there's a lot of modeling on the wall, but with these buildings as well, of course. Bless you. And it's easy. So I don't know if that kind of answers your question, or if you have any kind of follow-up question about it.
Yeah, I think it's, yeah.
Okay. Sana says, right now I am playing around with the negatives and trim it on the outsides. Is that a good approach? I like the insides, but like a more strict form on the outside right now. Is this fighting the whole system of? No, it's not, because as long as, okay, think of it. I'm just jumping through words. Don't try to be, never try to be purist. Do you know what purist is? Like someone who tries to keep either some sort of ideology without changing it, right? Don't try to be purist throughout any kind of process of design. You choose whatever tool you think is fine, and it is in this case. Does it? Wait, how did you phrase it? Does it destroy Game of Life? Wait, I'm trying to. Yeah, there we go. Is this fighting the whole system of Game of Life? No, it's not. The Game of Life system as it is now is just used to create some sort of a pattern with logic for connections, right? So the thing that we get from this, and this is not Game of Life system anymore because we have been changing the rules quite a bit, haven't we? So that's that, first of all. Second of all, it's messing around with no, it's not messing around. We are using the Game of Life system to generate a pattern for the volume. And then what we do with that pattern, a three-dimensional pattern, what we do with that pattern is absolutely up to us. So you can carve it and you can change it and twist it and bend it. Once you have baked it out, or not even baked it out, once the simulation for Game of Life has ended, then it's not, Game of Life anymore. Then it's just some form that you work with, right? Clay. It's just clay. So this part is quite easy for the students to do, to get. The part of, if you simulate something in Kangaroo and you bake it out, then it's not, Kangaroo anymore, and it's fine to change it as much as you want. Same thing with Game of Life. But the troubling thing, like what I see the students have a lot of troubles doing, is what's called killing your darlings. Are you familiar with that term? And any
Yes.
one of you?
Yeah.
Yes. So killing your darlings. It's something that early on is very hard for students to do, right? If you kind of, let's say I like this form, right? Like let's say this form, like just visually looking at it, let me hide the points. Visually looking at it, this form is nice. It has this kind of vertical, I can even make it nicer by baking it out, actually. Default, like that, and just running some sort of stupid emap on it, or, to just, oh, look how shiny it is. So let's say this form becomes my darling, something that I really, enjoy looking at, and it's something that I find to be quite successful with this kind of Cellular Automata approach. Even if it's not the case, doesn't matter. It's just to prove a point. And then once I start developing it into a building, once I start developing it into a building, I see that, oh shit, nothing fits. It either needs to be this kind of humongous building where a person is, you know, this teeny tiny, you know, this teeny tiny box is a person next to the building, or I don't know, I need to just destroy the insides of it. And this is where I see the students get a lot of problems when they need to destroy, you know, kind of completely change the thing that they like. And the thing is that you shouldn't think about it like you're destroying it. You're just introducing another iteration for it. And some iterations make fast jumps, like long jumps, where you can't really see any resemblances between the two steps. And other iterations, you can't really see any difference between two steps. You know, those make really small jumps. But this is how you create better and better versions of your building as you're progressing. So that's an important, you know, thing. Killing your darlings. Wait, what was the question? Negatives and yeah. So Sana, you're working exactly correctly, in a correct way with this script. At least this is how I would be working with it. It's you create a pattern that you find pleasing, and in this case, just by looking at it, like at what I came up with, is I enjoy like these three holes, for instance, here, right? And I know that, you know, that kind of rule set will always generate, from time to time, they will generate this pattern. And then I can say that, well, these three holes are, you know, some sort of windows or some sort of openings in my building, and kind of start letting my imagination go loose with it. In your case, you're trimming the outside of the building and trimming the inside of the building. Once you found a nice pattern that it makes, that's perfect. That's how I think you should be working on it. The only thing is, at this stage, don't think in terms of floors and windows and so on. Think in terms of levels, openings, and connectivity of spaces. So the longest time with this kind of a structure, I would spend the longest time with a clipping plane, for sure. Just going through it and going, okay, I can place a floor slab here. Not in the blue stuff. The blue stuff is inside of the walls, but on the outside. I can place some floor slabs here. And then maybe here, something like here, could be the second level, you know, in between these walls. I could start placing some surfaces here later, you know, and then just looking at what kind of space I get, you know, by just moving the God damn it, the clipping plane, moving it back and forth in the plan, and also moving it back and forth in the section. Just looking at, oh, this is a cozy little space here, and does it open up? Oh yeah, perfect. It opens up, right? So I'm talking about the one on the left-hand side, this hole here. As I'm moving the clipping plane, you can see how it opens up, right, to the outside. And then there is this kind of a small enclosure here, which also opens up, and then it closes, but opens up in another part. So it is like a cave system, but this whole area here can be some sort of a viewing deck, right? So this is an interesting, let me delete the clipping plane. This is an interesting area to be in, especially if I were to change the lens length to something more suitable for this, 30 degrees, right?
How do you make the clipping plane like update as soon as you move it? Because mine just updates when I release it.
Really?
Yeah, maybe Yes. No, now it works. Maybe it was just lagging.
Perhaps it was lagging. If you have a very heavy mesh, then it might be lagging. Because usually it updates quite smoothly. So this is going to be, what you're going to be doing with what I would definitely suggest you be doing with this structure. Not just looking at the outside shape, but also looking at the inside spaces, and imagining, how you would fit some sort of a function in them. Right now, don't think about it as, oh no, this this area doesn't have a flat floor. That's not a problem. Adding a flat floor is easy. Rather think about what's open, what's closed, what you'll have the possibility to close, what you won't have a possibility. Well, actually, you have a possibility to close anything, right? It's just modeling. But just keep looking at it from different sections and making sure that it all works as a building. And also, goddamn, the sections in these structures, the sections are pretty nice. I mean, they can be really nice. Person just here, just walking, staircase here, continue walking, on this level. There's a hole here and will need to be filled in, but that's not a problem. Does that, okay, I need to double check with you guys. Does that make sense? Well, what I've said.
Yes.
I mean, do you?
I think so.
What do we have to think about regarding wall thickness in later stages? Feels like it easily can get large volumes in this. Is this something we have to at least have in mind? Wait, let me, I'm trying to, what do we have to think about? What do we have to think about regarding wall thickness in later stages? Regarding wall thickness in later stages, where walls are thick, you can do storage. So you can make them hollow, right? For instance, let me grab the clipping plane again. Let's see, thick wall. Yeah, for instance, this guy is quite thick, right? So you can treat this one as print screen, right? There we go, file, new, okay. So at later stages, you will, let's say you have a section like this, right? So at later stages, you will say that, okay, this is a floor slab, right? So you just create a surface here. And that's a floor slab, meaning a person can walk in here and then kind of, then you can kind of break this open, and the person can continue on walking here, which is also a floor slab. So that's one part. And also here, let's say the thickness here, I don't know what kind of thickness it is here, because that's up for you to decide, how you're going to scale your form. But let's say the thickness here is a meter, right? Just, I don't know, any number, 1 meter. So that means that the thickness here is like 2.5 meters. So what you can do is you can say that, okay, inside of my walls, there is going to be this pocket here, right? And there is going to be this kind of a door opening. Let me zoom in so that it's easier to see. so there is going to be a door opening, and there is going to be a pocket inside, and then you can put all of your storage, ventilation shafts and shit like that inside of this cavity. And this is exactly what we've done with the tower project that I've shown. Very good architecture company. Projects, quickly, just to show real fast. Open image, new tab. Well, that's Can I please open image, new tab? Nice. Oh no, never mind. It's fine. So notice how the thickness of the walls is always the same, but in between the walls there is this kind of a piping and bracing, and there's even quite a disgusting one here, and stuff is happening. So you can put all of your communications inside of the walls, and also storage and stuff like that. If that was the question, I'm not sure if I understood the question correctly. Yes, okay. And then you just add, it feels like it easily can get large volumes. Is this something we have to at least have in mind? This is something that you definitely should have in mind with this. The scale of the structure, right? So let me just repeat it real quick, because this is important. This thing can be 100 meters long, right? Let me, how do we do this? There we go, print screen. Print screen, Photoshop, there we go. So this thing can be 100 meters long, right? So, 100, which means that the person is something like, okay, if that is 50, that's 25, that's 12.5, that's 6.25, that's 3.125. So a person is something like that, right? If I decide that this building is 100 meters long, and maybe it's a little bit too much for a naturum, maybe it's a little bit too big. If I then say that this building, no, it's not 100 meters long, it's actually 50 meters long, that means my person is twice as big. So it's, like that. Maybe it's a little bit better. What if I decrease it even more? What if I say 25 meters long? Then my person is, wait, if that is 25, that's 12, then that's 6.25, 3.125, something like that. So the person is going to be this tall. Okay, well, something like that, right? Okay, but once we reach like 25 meters, then the person will not fit through all of these openings, right? Through all of these holes. And those holes will become windows rather than doorways later on the stage of the project, unless you come in with a cylinder of some sorts later, and you just cram in that cylinder in that opening and just do Boolean difference and carve it out for the person to move through, right? So the bigger you get, basically the bigger the cell, each voxel is, right? Less of them you can have, right? So less resolution your building will have. The smaller each voxel is, the more you will need to kind of carve into the structure later on to be able to fit a person in. There's no correct answer in doing this. I'm really interested to see what you come up with. And when it comes down to opening and closing the holes, you know, to make it climate controlled, don't worry about that part whatsoever right now. I have shown you how to do that yesterday. You know, how to create those surfaces yesterday. Well, really briefly, but I will be showing that again and again and again throughout this course. So don't worry about what's open, you know, about adding more stuff to the structure. The first part is going to be having the form. Second part is going to be introducing the landscape condition to the form, or maybe it's, you know, something like this. And third part is going to be how the hell does your building connect to the landscape, right? What's the connection between the building and the landscape? So that's going to be the third part. That's a very ugly connection here. Looks like a freaking elephant.
I had a question about, or
yeah.
like a thought about like how you sculpt it. Could you, because I had an idea, because instead of just using volumes to subtract and limit how the shape grows, like we used the cylinders yesterday, if you could just, it's very manual, but if you could just take the points and bake the points, and then just remove and add the points as you feel, and then just then reference in them again in Grasshopper to make the cocoon mesh.
Absolutely.
The result would be the same, right?
Yes. Oh. Yes, the result, it's all about adding and removing points, right? So you can either do it manually, you know, just adding and deleting the points by hand, or you can use the you know, cylinder shape or whatnot to remove the points.
Because there's no easy way to remove single points in Grasshopper, right?
Single points, no.
So more an area of points.
Yeah, it's more like an area. For a single point, you would need to do the same, you know, kind of draw a sphere around the single point. Yeah. That's exactly why I showed you like those two variations, you know, one where I've just added points manually, and the other one where I've removed the points with volumes rather than, you know, deleting them. But with combination of those two, you should be able to, you know, produce any form that, you know, that you like, that you enjoy, and that you think would work spatially. So think about, I keep repeating this, and always remember, if I'm repeating something constantly, it's because I find it very important. So think about the space, right? And about the form and the space. So that's two main goals. What's the experience, right? What would the experience be? And when you're thinking about the space and the form, always in the back of your head, you should have the scale, you know, of this thing. How big is it? Is it going to be 1 kilometer long? Hopefully not. Don't do 1 kilometer long building. That would be too much for a Naturum. We don't have that budget. Any more questions? We still have like 2.5 minutes left.
Well, it's not really a question. I asked you yesterday about the cell sizes for the cocoon, and I tried to do it with different other cell sizes than 10. Yeah. And it works as long as they're multiples of 10.
Yes, yes, it is.
But it becomes very funny.
Yeah, exactly.
But they all keep, like, they still manage to attach to each other, just in a completely different way.
Yes, that is correct, and it's how do I explain it? It's not like it's accidentally working. If that makes sense. I mean, it's breaking, right? The fact that the cells are larger than the charges, that's breaking it, but it's still, as long as it's a multiple, it's still going to work, simply because of the math that is. I won't start. No. I won't start drawing the math.
It doesn't really break because like you get exactly the same shape, just much thinner or thicker. So if you have
there won't be any self intersections or what stuff like that. That's not the point. It's going to start ignoring a few points here and there, and also it's going to be overly. Yeah, did you say getting thinner? It's going to get overly thin.
Yeah. I suppose it gets even more like just like some kind of just crazy shape. But every point that is included in the original is still included.
Still included. Okay,
yeah,
I didn't know that it does that.
Because the point charge is still the same. So the point charge reaches 10 millimeters, and the points are every 10 millimeters.
Oh, okay.
So it's just the cell size. So you can add things between. Like you get an empty cell or like an empty spot between.
Oh, you mean if you decrease the cell size? Wait, let's have a call again. Just a second to record this. So I've already mentioned this, but Cocoon plugin in itself, this battery right here, this node, works with what's called the marching cubes algorithm, right? Remember when I showed you, I think it was last week, marching cubes algorithm, where I've shown you these like images of the scanned gunshot wound and stuff like that, and basically working within the voxels and using this kind of a possible library of polygons to populate those voxels and basically wrap a point grid around with a mesh. And thus, you can create always a clean mesh with really shitty topology, by the way. Right now, you know what topology is. So the topology of these meshes created by Cocoon and also from any kind of a marching cubes algorithm is bad, as you can see here. There can be much nicer ways of how to create polygons on a sphere. But the nice thing about it is that the meshes are always going to be closed polygon meshes, and they're always going to be 3D printable. So back to what I'm teaching the master students. Since marching cubes algorithm, Cocoon in general, works with 15 cases on what kind of polygons it can add to any kind of a voxel. So these empty boxes here represent voxels, right? And these polygons represent, chosen cases from this table. There are 15 different cases. One of them is empty, right? Case 0, and others are, one triangle, two triangles, and so on. And it kind of goes through all of the different voxels in the space and chooses whether or not it needs to put in a shape. And if it needs to put in a shape, then it will choose what kind of case it needs to use. Right. So that got me thinking, what if we were to say that these shapes, since all you need to have is these 14 different versions of a shape to be able to produce any kind of form, right? Forms like these also are produced by these shapes. So any kind of form can be produced by these shapes. What if we were to say that these are architectural elements? And what if we were to model them out and kind of replicate the marching cubes algorithm in Grasshopper without any plugin, but rather, by just a Grasshopper definition with some sort of anemone loop. And then come on, minimize, there we go. And then I started working on it. And there's a video, Rhino Hard Surface Modeling, Marching Cubes Elements on my YouTube, where I kind of just go through all 14 or 15 of these cases and just model them out and see how these can be some sort of a more, not necessarily architectural, but more structural thickened elements. And I'm modeling these out in a way that we would be able to connect them with screws, right? With 3mm screws. So this is a like almost 3-hour video, and it's sped up. So if you just want to see me model for 3 hours straight, then you can kind of, if you really want to, if you can't get to sleep or anything like that, then you can just look at me model until you fall asleep. That's very romantic. So I went through all of these cases here, the library of elements, 15 elements, and I kept modeling them, right? And in different styles and then so on. I just was trying it out. And by the end I had, where is it? By the end I had like 15 different elements that I've used to generate this shape and created a V-Ray material for them and an environment to render out, where is it? To render out this kind of a manga style, comic book style render of it, right? So that's this video. And then we started the course, because I just tested it out and it seemed like it works, right? So we started the course, and thankfully we had 14 students in the course, which means we have 14 elements, we have 14 students. Each student needs to model out one element by themselves, which was a very nice thing indeed. And blah, blah, blah. So tutorials for that course. And by the end, we had a work review and also a webinar later on after the first work review. So this is like the mid review for that master's course, where I just go through the models that the students have modeled out and talk about the shapes there. And you can see some cocoon stuff going on there. So some shapes there. And then we had the webinar where the models were adjusted, and this is the current library, which is going to be printed out. So now if you'll see the master students in the 3D print lab, then you'll notice that they are printing out these elements because they need 700 of these. And each of these elements takes like 5 hours to print. They're having fun there. But the aim is, come on. The aim is that we, for the spring exhibition, if it's going to be, existing, we're going to have this structure built. And it's going to be slightly above 1 meter high, made out of these elements, right? So you don't need to think about these kind of cocoon meshes as just, this consistent, perfectly smooth mesh. These can be treated as, do I have a bigger picture of this? Let me just quickly find if I have a bigger picture of this. Other, yeah, I have it here. So then these can be regarded as meshes that are, or forms that are made out of 14 different elements, right? Any feedback? Do you get it? Or just tell me if you got it. Yeah, and all of these are connected through screw holes. Actually, I have some of them printed out. Wait, let me stop sharing in just a second. So I'm back. So some of these are printed out, you know, stuff like this. Can't really see it. But the thing is that all of them have these kind of a, how do I show it? Maybe this is better. All of these have these holes on the edges. And if we use those holes, we can connect. So this is like this is three pieces connected to each other, meaning that I have bought 700 screws for the students, and they're printing 600 elements, and by the end, the model is going to be pretty damn heavy. And also we have like 2 liters of black paint, so that it all looks very, you know, architecturally modeling. Why I'm showing this to you is so that you don't think of the structures, you know, of what you get from Grasshopper or from Rhino as just some sort of a single infinitely strong clay thing. It can be made out of parts, right? So it's not necessary to think of it as something perfectly smooth, like in the, share the screen again. It doesn't, you don't need to think of it as something that is perfectly smooth, like in the render here, right? This can be made out of parts, but that's for later. This is just me kind of jumping in front of the future problematic that you might encounter. So now we can jump back to our stuff, and I'll just give you a really quick, not even a tutorial, but rather more of an explanation of Cocoon. So now we know that Cocoon by itself, it works with these voxels. And if I actually bake out just the Cocoon mesh and look at it, no, wait, let me disconnect it like so and use ISO value of 0.5. Just a second. And then I bake it out. So this one. Here, it's very hard to actually see it, right? In within this mesh. Maybe in some places like this, it's possible to see it, but it is following, it is using this table of elements to construct the Cocoon mesh, right? At least the first start of the Cocoon mesh. But, it's an important but, once this mesh is constructed, there is a secondary tool in Cocoon that's called Refine. And if I connect it to the oh yeah, well, 0.2. Why are you now not working? Oh no. Oh no. Oh no. Wait. Now it stopped working. Why did I break it? I just broke it, didn't I? Oh, that's because I plugged in the wrong output. Wait. Let me jump back here. You don't plug in the mesh to the refine output. You plug in the refinement data to the refine input, like that. And now it's gonna work. So back to here. very important tool here is Refine, which solves a few problems that Cocoon Mesh by default, or marching cubes, I should say marching cubes, Mesh by default has. First of which is topology, right? By itself, let me big this out again. By itself, the Cocoon Mesh will, well, the marching cubes mesh will always try to fit in a grid, right? So basically, we'll try to rebuild your structure with a grid. If I look at it from the top view, it's even easier to see, you know, that this is all made from some sort of a 3D voxel space, so from some sort of a grid. And for curvilinear, for curving shapes, it makes no sense, right? Because the lines don't follow the curve, so it all kind of starts breaking apart, and it's a little bit jagged and so on. So that's one problem. Second problem is these kind of really, really thin triangles that sometimes appear, especially like, you know, this guy right here. Topologically speaking, this is shit. Like, this is really bad. Having this kind of really sharp small triangle is really bad. So what Cocoon does, rather not Cocoon, but Refine does, it starts solving, first of all, it solves the sizes of the triangles, right? So with our settings here that we have, and subdivision, I now have it set to 1, but I can choose it to be 0. So first of all, it will go in and it will change the size of the triangles just so that they all are kind of the same size, right? That's the first thing that Cocoon does. And it's nice that it does that. And it's called balance passes. This is, you know, how many times it tries to solve it. For instance, if I were to change balance passes to 1, well, it still does a pretty good job. Let's go for 0. Okay, if it's 0, you can start seeing that some triangles are much smaller than others, but it's still not that bad, right? Well, sometimes bad, sometimes not that bad. So there's a combo of 2 things that are fixing it. One is the smoothing, and the other one is balance passes. If both of these are turned off, if both of these are set to 0, you can see that the triangles become more and more distorted, right? They are more and more too thin or too thick. By itself, refinement already fixes the really thin triangles. It just does that automatically. Even if I have everything turned off, like that. Even if I have everything turned off, it already fixes the really small triangles. But other than that, it doesn't do anything else. So now, when I have everything set to 0, let me show you what different things do one by one, and I'll start from the bottom. So subdivisions, sub D, right? Let's choose this triangle here, this one here. If I have subdivision set to be 1, that triangle that we had will become 4 triangles. So all that subdivisions does, it just adds much more resolution for the refine to work with, right? So that's all that it does. It just adds, you know, more polygons, which is nice, right? Then we have another slider, which is valence passes. And valence, as I mentioned before, is, for instance, sorry, this point right here it has valence of 6, meaning it has 6 polygons that are connecting to it. And if I look hard enough, for instance, this point here has valence of 5, right? So it's only 5 polygons that are connecting to it. And I believe if we were to look even harder, we would somewhere see a polygon. Yeah, for instance, not a polygon, but a point that has valence of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What? 9 or 10? 3, 3, 3, 9. So valence of 9. So what valence passes does, if I give it like 10, it tries to make everything to have the same valence, right? Same amount of points. It will not succeed perfectly, as you can see in some places here. Even by looking at it like so, I can see that, yeah, there's probably some some points which have a different amount of polygons, a different count of polygons surrounding them, but it's doing its best, right? So give it a break. And those points in this kind of structure are called singularities. And we already learned about singularities a little bit. So that's valence passes. So it tries to clean up the topology of the mesh as best as it can, as well as it can. Then we have the next one, which is Laplacian smoothing. And what Laplacian smoothing does, and actually, let me Google that for you. Laplacian smoothing. So what Laplacian smoothing does, it moves all of the points closer to all of their neighbors, meaning that if you don't anchor your horse, in this case, anywhere, and where you don't say that, well, smooth it out, but don't move the points too much, eventually it's just going to become a single point, right? It's going to smooth until it's just a single point. So it smooths, but it also shrinks the surface as it's moving it. So as I'm going to be increasing Laplacian smoothing passes, see how the surface becomes thinner and thinner, but at the same time it becomes smoother and smoother. And this is part of the tutorial which I wanted to show you, where you're smoothing it out, but at the same time you're sacrificing a little bit of accuracy, right, of the structure. Then we have sample tolerance. And I believe that the sample tolerance, and I might be wrong, I'm not sure about these two, but one of them or both of them is how far each point can move from its original position. So sample tolerance, if I turn it up to 0.1, and then I turn on the sample size to 1, nothing changes. Oh yeah, and nothing changes because I'm not saying how many steps needed to be taken. I'm saying, you know, please don't move the points further than probably 1, right? 1 millimeter. If you need to move them by more than 1, then, you know, don't. But I'm not saying how many times should it check. So I'm implementing the rules here, but I'm not specifying that those rules should be applied to the model. So I can apply those rules through samples by specifying that, well, check once, you know, check once. And when I turn on the samples, you can see that the structure is almost back to what it was before. And that's simply because we are kind of locking the smoothing, valence passes, and valence passes, we're locking these two values down because we're not letting the points to be moved more than by 1 millimeter. And I can do like 10 samples and it's going to be quite the same, you know, it's even worse, right? So to get a perfectly smooth surface, which, oh, and it also, this is not pure, like, this is not refined whatsoever. So to make a perfectly smooth surface, a perfectly smooth mesh, you need to sacrifice some accuracy. And it's not just for the mesh, it's for any surface. You sacrifice accuracy. So if I turn off the samples, if I have this set to be 0, we're back to having a perfectly smooth, really nice shape. And I can even introduce 2 as my subdivisions. Please don't do that. That is way too much. But this is just to show you, how smooth it can get. Display, turn off preview mesh edges. This is how it looks like. Where is it? There we go. Is that clear? Or did I mess up explaining something? Okay, so that's that. Now on to, I don't know how much time we have, probably more than 10 minutes. So now it's time for questions. Question and answer session about Cocoon and anything related to Cocoon. While you're asking questions, or if you have any questions, then shoot. If you don't, just look at me model something. Seriously, no, like everything is so clear with Cocoon, and no questions whatsoever. I guess Cocoon is one of those not programs. What am I saying? One of those plugins which are pretty much, straightforward. Right now, what I'm doing is I'm just referencing in the B-reps. So I've just created 2 boxes just to show you additional functionality of Cocoon. I'm just creating 2 boxes, and I will be going to my mesh, Cocoon, and I'll find B-rep charge, because I already showed you curve charge and point charge. So I'll be showing B-rep charge now. Works in exactly the same way. I'll give it a radius of like, I don't know, 4, whatever. Something like that. So that's my B-rep charge. Why does it still complain? S failed. Okay, so what's S? S is strength, isn't it? Yes, it's strength. So I'll just connect the same strength as I'm using for the curves for my B-rep. And holding down the shift key, I'll just connect it to my Cocoon solver. And then wait. And then wait some more. There we go. So you can use B-reps for this kind of a workflow as well. Not necessarily boxes, by the way. Can be anything you want. And this is if I type in what? Closed double precision polygon mesh, valid mesh, 3D printable. Well, kinda 3D printable. Remember the thinnest walls that you can have, and this is probably going to be way too thin if we were to print this as 7 centimeters. Can you make Cocoon smooth out on a surface? Can you make Cocoon smooth out on a surface like they did on the master project? Wait, give me a second to digest the question. Okay, master project, first of all. Going from flat to flowing. Which one was that? Was it one of these? Yes. Was it the one in the circle in the bottom? Okay, so can you combine rectilinear shapes of cocoon with curvilinear shapes of cocoon with rectilinear shapes of a box, for instance, or a cylinder? Yes, you can. But my biggest criticism that I had for one of those projects, I believe it was, let me find it. My biggest criticism during the first review of these elements for this project was that the aesthetics of it didn't match, right? You could do a contrast-based approach where you have one type of structure and you have another type. Let's say you have a blob and you have a box, and the blob is kind of climbing on top of a box or whatnot, you know, something like that. You can have that. But in this case, the cocoon, and this is not cocoon, this is topologically optimized mesh, but let's just say it's cocoon because it has the same aesthetic. In this case, it was used as a complete part, like a substitute part of the element here. And suddenly it falls out of place, right? It suddenly feels quite alien to the element because even those connections here in the top where it connects to the plates, they don't really, kind of work. So my suggestion was, in this case, for this particular model, was to remodel it, extract the cocoon part and remodel the brackets from the cocoon mesh into a poly surface. And then use that poly surface as the actual bracing so that it has the same aesthetical kind of quality, right? Because if you want to merge two different aesthetics together, then it is then you need to be much more mindful of how you're merging them and how they interact. It cannot be just plop in place and yeah, contrast. No, it doesn't work that way. To be able to merge a B-rep with a cocoon shape, you would need to use Boolean union. And to be able to use Boolean union, the shape would need to be a NURBS polysurface. If I were to select this mesh and go mesh to NURB, enter, then it would crash. Because every single triangle here would need to become a separate surface. So then there's a big question of resolution, of how many how many meshes, how many mesh faces can you have to have that kind of approach. Even something like this, so this is without any subdivisions here. Even something like this is already pretty damn heavy and would be very hard to merge. So, okay, the short answer to the, right now I've given you a long answer without a concrete, kind of endpoint. The short answer is, can you make, can you join cocoon mesh with NURBS polysurface? Absolutely. The long answer, well, not the long answer, but the continuation of the short answer is absolutely, but you need to be very mindful of the limitations of the computer, first of all. So you'll be limited by the, oh my God, by how many surfaces you can have at the same time on the screen, right? And also another limitation is the composition, right? working with composition. So that it's not something that just, you know, mindlessly was plopped into place without any regard to the logic of things. The way I would approach this, for instance, is let's say if I go to top view and I want to merge these tentacles with the boxes, right, rather than smoothing out the boxes, I would probably go to mesh tools. I would choose to, where is the freaking extract mesh faces? I would choose to extract mesh faces like that. So these guys get extracted. So now these are separated from, you know, from this mesh. So I have extracted them, I will hide them. Then I would extract more, extract mesh faces, extract more here. And come on, extract here. And then I would delete this part, right? So what I end up with, show selected. What I end up with is this mesh, right? Which has the center part, which I will not touch, right? This will stay as a mesh. And it has these two parts here, which can be changed into mesh to NURB, into NURBS polysurfaces, right? So then what I would need to do is I would need to hide this, fill this up, and this is less than a minute left. Yeah, I know. So I'm rushing. I will fill these up into closed volumes by hand, each of them, use Boolean union, and then join it back, make it back into a mesh and join it back to this mesh here. Long, a long thing, but that would work. Let's have a second call for about Rhino now. This is a good transition into Rhino modeling. So wait, I'll just finish up with this one real quick, right? So I mentioned that I would be extracting these parts, like so separating the mesh into a part that I don't need to be a polysurface, parts that I need to be polysurfaces, and then probably some boxes here and there, something like that, right? So to join it up, I would, and let's say this whole part doesn't exist just to save some time, I would need this, these guys to be closed polysurfaces. And there's no quick way on how to do it. It's just taking a freaking surface from 3 or 4 corner points. And slowly but surely, and it doesn't need to be pretty, it just needs to be closed. So slowly but surely, well, maybe I'll choose this one now, stitching it into a closed polysurface. And I would do that for this, for all of the openings, join them up so that they're closed, connect them with the box by using Boolean union. Then I would, so once it's connected, it would be a box with some stuff sticking out. Then I would delete the surfaces or extract the surfaces to open it up again. Mesh all of this, create a mesh, join it back with this mesh, and then I have a sharp box here and a mesh sticking into it in a very, very clean way. So that's how I would do it. Or you can say that by the end of this, I will want it to be NURBS polysurface rather than a mesh. That's fine as well. Then what you can do, actually this is going to be faster. Let me change this into NURBS, mesh to NURB. So then I would change this one as well to a NURBS polysurface because I need to. Join this bad boy up. So now it's a single shape. You can see that it's not the fastest now. And I would go into the top view, right click, wireframe, and I would choose to, oh yeah, I have some trash there. I would choose to trim. So I would select my box, type in trim, and trim away the polysurface here with the box. And then back to perspective view. I would choose the polysurface. Come on, escape. Shush. I would choose the polysurface. I would type in trim again. And then this is where it gets a little bit tricky, right? Because I need to trim out the holes in the box, right? For these guys to connect. So I would, Jesus Christ. Okay, there we go. So I would choose to trim and then click inside. By looking inside of the box, I would click inside of the regions to open it up. Like that, like that. Don't remember if I already trimmed this, probably I have. So it's 4, yeah, that's good. Enter. So now what I have here is if I move this away, I have a box which has openings, trimmed out openings, and I have these tubes that are waiting to connect to the box. So I can just simply join. Two surfaces joined into one open polysurface. Notice how slow it is for me. So be prepared to become very, very patient if you're using this approach. Extract the surface. And that's and that's how it, how it would look like. We can play a game where we kind of go through this tunnel cave system. Anyway, cool. Say cool. Cool. So trimming is basically like a ghetto Boolean difference, or sorry, trimming and joining is like ghetto Boolean union that you can use if you don't want to you don't want to make the forms closed at this stage. Okay, delete. So now we're done with this. Let me just save it and save this one. New file, no template. Where is my cocoon? Hello, 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 hello. Kangaroo, cocoon, and we have cocoon. Am I blind? Kangaroo, morning. Wait. Oh, yeah, sure. There it is. Scrolling helps. So I'll just upload it to the chat so that you can download. All right. Last thing that I wanted to show for this tutorial session, for the second week of the tutorials, is network surface. Those of you who want to make blobs, Those of you who want to make blobs, is Axel here? No, we need Axel to be here. Axel. Axel, there we go. Invite to meeting. Join us. Okay. Is Axel here now? I don't see him in the list. Well, it doesn't matter. Axel can, nice. Yeah, I assume you're in the meeting if you're saying nice. So I'll be showing you how to, how to use network surface. And we have been using network surface with Olga to create this competition, which is entry, which is going to be built sometime. I don't like. I hate how they're not concrete about it, but so this is something that is why I'm saying that it's going to be built is because I need you to know that this is something that is buildable, right? Not just some sort of a Grasshopper weird thing. So we've been using network surface to create a cage, and we have used was it bamboo or something like that? I think it was bamboo to create this kind of woven basket structure, right? So this blob here is created by using like these tree houses. For artists, they are created in two skins. The inner skin is fabric material and the outer skin is a woven bamboo structure, right? Easy as that. And it's created, the form itself is created by using network surface. And I believe this is something that is important to kind of show you. Oh yeah, and there's detailing here and all of the anchoring, because they really needed us to prove that this thing can be built. So network surface. The tool for it is located, am I recording? Yes. The tool for it is located here in the surface creation menu. It's the third tool, right? So you have surface from corner points, planar surface, and then you have network surface from network of curves. And the simplest one to show you is, let's just draw a line segment that is 100 millimeters long, right? One line segment, 100 millimeters long, and I'll copy it to the side by another 100 millimeters, right? So I have two line segments here. And then I'll do it again, copy it again by 100. So we have three line segments, and in between them, we have 100 millimeters. All right. And then I will grab another line tool and just draw two straight lines here. So these are just two lines in the other direction. And I'll just draw one more straight line between the midpoint to midpoint here, like so. So we have three lines going in one direction, and we have three lines going in the other direction. And we don't need Grasshopper for this. This is a Rhino tutorial. I can select these lines now, and I can choose the surface from network of curves, right? I choose that. It tells me, okay, this is going to be A, B, C, and D, and I'm going to make a surface like this for you. I hit OK, and I check the shaded view, and voila, we have just made a flat rectangle. Okay. The strength of it is that if I were to say, how do we do this? let me delete the middle edge here, and let me just say rebuild. And I'll just give it like 5 points for each curve. So I'll rebuild the curves by 5 points. And I'll just grab the, I'll just grab the center points and just move them up. And maybe the middle one can be moved down like that, right? Something like this. And then what I'm going to do is I'm going to take the, not the control point curve, but rather the curve interpolate points, the second tool. Remember, one is using the points as control points, the other one is forcing the curve to go through the control points, right? So curve interpolate points. I'll go through midpoint, midpoint, hello, midpoint, midpoint, like that. And I'll rebuild the curve again, and I'll give it like 10 points, something more points here, and just kind of mess around with it a little bit. Something like that. Maybe this goes down, something like this, right? Well, honestly, this shouldn't be, like this part should be a little bit, better controlled, but for this tutorial, it's gonna be fine. Then I can still do the same thing. I can select all of these and I can choose surface from network of curves. As long as my curves are making a grid, it's going to produce a surface through those curves, right? Clear so far? Or do I need to explain something in anything that I've said in more detail? Where's the chat? Ah. Kinda, yeah. I think about the shape as a number of sections in 2 directions. So, yes. So I'm just making the outline basically, a bunch of sections. So in the case of that treehouse, what we've done was I've created, I believe I've started with an ellipse shape, something like this, right? And another one higher up, something like this. And we have rebuilt those 2 ellipses with certain amount of points. I think like, well, I'll do 5, but it was probably something else. And kind of messed around with the form of them, like that, something like this, whatever, doesn't matter, right? So now I immediately know that this is going to be my one direction for the curves, right? This is going to be one direction. Then what I did was I've created these kind of straight lines. So I've just said, okay, so from this point to this point, I want a straight line. Then from this point to this point, straight line. From here to here, I want a straight line. Oh, maybe to here. I want a straight line. And then I'll just give it one more. I think I had like, yeah, the red ones were lines at one direction, and the blue ones were lines at the other direction, right? So I've created a bunch of them. But for this tutorial, I'll just show with 4, right? With 4 lines. And I've just took those lines and rebuilt them. So I've used rebuild with, I don't know, like 4 or oh, no, not 0, 4. Shit. That needs to be 4. That needs to be 3, sorry. Panic. 3 and 5. There we go. With 5 points. And I've just took some of those points, moved them out, and kind of gave it sections that I would like to see on that particular portion of the surface, right? So let's say I want this guy to bend inwards and this guy, or these two guys to bend outwards for this shape at this portion of the surface. So I got this. And then I have selected all of it and chose network of curves. And it just makes a basket for me like that. And then I will create a circle here, like this. And I'll just move the circle down somewhere here, maybe closer, somewhere here. And then I'll move the circle up to somewhere here, right? So, or copy rather the circle up. So I'll choose these two circles, make planar surface out of them, like that, and use blend SRF, right? To blend these circles with the edge of the surface. So it does that. So if it does that, it means that my circles are a little, my circle is a little bit too high, too low. So it doesn't have enough room to be able to bend. But I can kind of control these sliders a little bit. And by controlling these sliders, I can control how it bends. So I think something like this. Yeah, I think something like this looks fine. I'll hit OK. Flip. Change object layer. So I have this going on. And then I'll do the same thing for the other one. Blend the SRF between this edge and the edge of the circle. I'll just make sure that they align properly. They seem to be aligning. Kinda. Yeah, that's actually good enough. Enter. Play around with the sliders until I have something that kind of works. Maybe this can be a little bit more fat here, a little bit less fat here. Hit OK. Select all of the surfaces. So the circle, the cap, the middle section, the cap here, and the circle here. I'll just move them to the side away from the curves. Join. Change object layer. So I have something like this. It doesn't seem like it's seamless. So let me double check. And this is where you use EMAP. This is for what you actually use EMAP. When something doesn't seem like it's seamless, but technically it should be seamless, then you use EMAP. EMAP, enter, select objects for environment map analysis, select, enter. Can't see a seam. Seems to be a pretty continuous surface, doesn't it? Okay, so that's how you create a blob. Thankfully, this worked. If this didn't work, I would just kind of close the meeting and stop recording and never show up again. So that's good that it works. So do you have any good tutorial for using the surface tool? Which surface tool? Oh, then the surface from network of curves. So this is basically the tutorial. You know what? On YouTube, search for shoe rhino tutorial. Those guys definitely use network. Yes. Shoe. So shoes definitely use a lot of network surface stuff. Sorry, surface from network of curves tools. You definitely use a lot of that. Alternative to this is just simply taking, let's say, a curve, top view, and let me just, so right now I'm working in top view, and I'm just going to draw out a line that is going to be 100 millimeters long as per usual. So a single line, and I'm just going to draw out some sort of a form here. Doesn't matter. Some sort of a form like that. I will move it slightly away from the line so that there's a little bit of a gap like this. And I'll just rotate it back in, sorry, rotate it back in perspective view like so that it's vertical. And then I can use array polar on it. Center of polar axis. I'll just choose the single vertical line that I have here, like this. Number of items 3, no, 5, something like that. Angle to fill 360 degrees. Yep. Enter, 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 and enter, enter. There we go. So I have this shape here, and then I don't need the center axis anymore. I can delete it. And I can mess around with the control points of each of these individual shapes any way I want. So I'll just mess around with one of them. Well, maybe two of them. This one is doing this, and maybe this one is doing also this. And perhaps this one is kind of lifting up a little bit. And I can loft them. That's not loft, that's lock. I can loft them. God damn it, that's lock again. Loft them. And here I need to make sure that when I'm trying to loft them, that closed loft is turned on, right? So that it makes this kind of a blip. Okay. And then I can cap to fill in the openings here and here. I believe then like I could solve this edge here by using fillet edge on it. Well, larger radius, like 10. Something like that, but you can see it starts making mistakes here and there, so it's not ideal. So my suggestion would be to actually use this approach with network surface and then using blending rather than lofting. Also, you have much more control with the network surface because you can control the top and the bottom as well. Can we fillet this guy though? Oh, one last thing to check. Explode, merge, SRF. Nah. So merge surface doesn't. Oh, it works for these two, but it didn't work for these two for some reason. So what merge surface? Oh wait, now it's all weird. Anyway, what merge surface does, it merges the, it creates one surface out of two, as long as they perfectly match up. So they need to perfectly match up to be merged into a single surface. But it's kind of, you know, you don't need to use it. Right, so now we're past 5. Before we finish, do you have any questions about, this kind of blobby shapes? Honestly, this would be my suggestion, to create the core of it, create a top and the bottom for it. And I've created the top and the bottom as a big circle. It doesn't need to be a big circle. It can be something, quite small. So it's not like the top of your blob will always need to have a very kind of flat circular shape. And yeah, and then just using blend surface. Blend surface is definitely your friend. It's something that makes seamless stuff really easily. Questions?